Hello, my name is Jordan Wise. I'm a student at Georgia Tech. We'll be presenting today on a paper titled Multi-Level Anomaly Detection in Industrial Control Systems via Packet Signatures and LSTM Networks. This paper is authored by Cheng Feng, Tingting Li, Depth Shana, all of Imperial College London. This paper was presented in 2017 at the 47th Annual IEEE IFIP International Conference on Dependable Systems and Networks. This paper the entirety of this paper can be viewed at this link. A little bit of background. First off, an ISC can be described as a combination of supervisory control and data acquisitions, or SCADA, distributed control systems, human-machine interfaces, and programmable logic controllers. Modern ICSs are a result of adaptations made from previous generations of ICSs. Previously, most ICSs tended to be air-gapped. As time went on, Smart ICT has been integrated into ICS where again, those old ICS systems had a lot of legacy hardware. That legacy hardware tended to be insecure by design, difficult to upgrade, and that integration between Smart ICT and ICS created a connection between the physical and cyber infrastructure. So in an indirect connection to the internet, no longer air-gapped, you could say. NIST provides three of what they see to be the main security issues posed to a modern ICS, and those are that they utilize insecure by design communication protocols. Insecure by design tends to mostly because they're outdated. Insecure network segregation access controls, and a lack of ICS-specific firewalls and anomaly detection systems. Cyber attacks against ICS can result in physical damage to critical infrastructure, and these attacks are on the rise. These stats are from ICS CERT. They talk about in 2013 there's 73 reported incidents, in 2014 245 reported incidents. That increase in that 1 year alone is 336%. 2015 they saw 295 reported incidents, which is 20% increase. Modern ICSs are composed of three parts. There's in this paper outlines a framework wherein modern ICS can be composed of three parts. There's the corporate network. So that corporate network provides business-to-business and business-to-customer services. VPN access into that network is almost always a factor. And then some corporate network resources will be directly exposed to the internet. There's the control network, which is connected to both the corporate network and the field network. That is where the command and control, or where devices like HMIs will serve as command and control interfaces to the field network. And the field network is where those assets tend to be, those physical assets. The paper lays out a common attack path, or the path of a common attack. It gives the example of corporate network compromise via social engineering, so something like a corporate employee receives a phishing email that grants them access to the corporate network. From the corporate network, the attacker moves laterally to a control network, and then once they have access to that control network, is able to make changes to logic and programs on the field devices and cause damage or compromise in that way. Intrusion detection systems, there have been a lot developed for conventional IT security networks, conventional corporate networks. They facilitate incident response. They allow real-time analysis of systems and real-time alerting. Some challenges. So while there have been a lot of conventional IDSs for IT networks, there are different challenges for developing an ICS-specific DNS or IDS. For example, there's a lot of ICS-specific communication protocols like DNP3 and Modbus. There aren't a lot of real-world ICS environments there aren't a lot of data sets from real-world ICS environments. Then there's the increased complexity stemming from need to correlate activity to physical processes. and physical process behavior is not entirely consistent in nature, which is just to say that traffic on these networks tend to be noisy. The paper does address some past ICS-specific IDS systems, though obviously this paper is not presenting the first ICS-specific IDS system. Those systems tended to either rely on model-based approach or a behavior-based approach. They did incorporate some ICS protocols, but they have limitations. The paper lays out a couple here. One is that they tended to be highly reliable on predefined models and signatures, which meant there was a high human preliminary effort in getting them set up. The models and signatures are based only on what has already been seen, so they were unable to detect and alert on things like 0 days. So anything it hasn't seen before, it's not going to be able to alert on. They tend to be highly tailored for specific protocols and systems, and with the breadth of protocols and systems that exist in ICS environments, there were gaps in compatibility. And then it talks about a low knowledge around temporal dependencies between packages, which is just saying that these dependencies are the least studied in the prevailing literature. Anomaly detection has been around for quite some time. The earliest IDS first got built models to capture normal system behavior. Later iterations incorporated more SCADA-specific protocols and utilized deep packet inspection, stateful intrusion detection frameworks, and open source IDS tools like Suricata. Machine learning techniques have been leveraged in recent solutions. The authors of this paper believe they are the first to propose a solution that utilizes a Bloom filter for package content level anomaly detection while enhancing their detection mechanisms with an extra LSTM, which long short-term memory network-based time series level detection, which I'll talk about later. On to the problem statement. What method should be used for detecting anomalies? This paper proposes utilizing two frameworks: package level anomaly detection, which evaluates the package for anomalous behavior only looking at that package and the different features that can be extracted from it. And then time series level anomaly detection, which looks at that package and a number of previously seen packages to try and attempt to determine the next package that it would see. Both models are trained solely using a dataset without instances of anomalous packages. Because this framework relies on understanding what normal looks like, it is able to detect unseen anomalies. So let's talk about package level anomaly detection and time series level anomaly detection. For package level anomaly detection, the model assumes that normal behavior of network packages exchanged between field devices can be observed given a sufficiently large time period. The time period tested will include only activity in an air-gapped environment. All of the package's features will be used to define its signature. So basically, a unique value is assigned to each of the different combinations of parameters that can make up the package. The outcome is expressed in a string format with a special character as the delimiter. For this paper, data set was split into a training set and validation set. And then this is where the Bloom filter is utilized to increase efficiency of signature storage and lookup. ICS network traffic monitors have limited memory and computing resources, and Bloom filters are data structure used to test if an element is a member of a set. Time series level anomaly detection. So after passing the Bloom filter anomaly detection, analysis related to observation of previous packages occur. An LSTM network is a type of recurrent neural network. It has special units called memory cells. Evidence has been presented that LSTM networks can outperform traditional RNN and feed-forward networks. They can memorize information for a certain number of time steps, and from that predict the behavior of the next time step. So these are the two detection frameworks or detection methods utilized for anomaly detection in this paper. Now we're going to talk a little about the stacked LSTM network-based anomaly detector, which is part of that time series level anomaly detection that we talked about earlier. Again, it's going to try to predict the next data point given past data points. It'll take the input of a time series, learn the feature representations, and then try to predict the next data point. Instead of trying to predict the next package itself, the model tries to predict the signature of the next package, and again, that signature is expressed in a string format. Network packages are passed through several LSTM layers to learn features. The model is trained to minimize the softmax loss function. And again, no anomalous packages are used in the training data set. If any of the packages used in the training set were to contain anomalous results, the model would be less able to successfully predict future normal packages. Instead, a feature is added to help account for normal network noise. This feature functions by tracking the number of times that an analyzed package has appeared in the training set. As can be seen in the figure, the process is easily understood. First, an analyzed package will be checked by the Bloom filter anomaly detector. If no anomalies are detected, it will be analyzed by the time series anomaly detector. All packages, whether normal or anomalous, will be used as input for the classification of further packages. Let's talk about the dataset utilized in this paper. The network data was captured from a SCADA system through a gas pipeline system. There were 274,628 packages total utilized in the dataset. The gas pipeline system was a small airtight pipeline connected to a compressor, a pressure meter, and a solenoid controlled relief valve. As you can see, some of those network packages were normal. About 214,000 were normal network packages, and 60,000 were packages associated with attacks. This particular SCADA system used the Modbus application layer protocol. Each package was broken down into to have 20 unique features. Those features were utilized in the training model. You can see those features here, things like address, function, length, time, command response. I'm not really going to go into them, but you can see what those features were. For example, there were 4 different categories of attacks. Those attacks were created using AutoIT automation. Those categories were command injection, response injection, denial of service, and reconnaissance. 60%, or the experiment used a 6:2 proportions, which is to say that 60% of the data is used in the training set, 20% is used in the validation set, and 20% is used for testing of the anomaly detection framework. Remember, the training set and the validation set don't contain anomalies, but there are anomalies in the testing set. To set up the Bloom filter, they first had to figure out what the continuous features in the packages of the data set. Remember, we had those of those 20 features. They determined that there were 9 continuous features that they were going to utilize. Those were the 5 PID control parameters. Those talked about those here. So the time interval between consecutive packages here at set point pressure measurement, and the 5 PID control measures. The 5 PID control measures were clustered together because they were strongly correlated. Time interval and interval time interval and CRC rate were divided into two groups using k-means clustering, and set point and pressure measurement did not have natural clusters. Time series level anomaly detection is that, we talked about this before, it's that stacked two-layer LSTM network trained with and without probabilistic noise. The stacked LSTM network model can be trained to be more robust to noisy inputs that look like anomalies. The false positive rate was set to 0.05. Training time was about 35 minutes. This was on a Linux machine with 3.4 gigahertz Intel CPUs and 14.6 gigabytes of memory. So this is saying that it took that Linux machine 35 minutes to process and be trained on the entire data set. The setting notes that this is an acceptable result or an acceptable training time because the training can always be done on a non-operational ICS node or mode. The average total time cost of making the classification using the combined framework is 0.03 milliseconds. Again, that's the same machine that the training was conducted on. For the anomaly detection results, they pulled on 4 metrics: precision, recall, accuracy, and F1 score, which we'll talk about in the next slide. So those 4 metrics are precision, recall, accuracy, F1 score. Precision is the probability of a detected, or the probability of it is the probability of a detected anomaly is correct. Recall measures the fraction of anomalies that are successfully identified. Accuracy is the fraction of data samples that are correctly classified. And the F1 score is a measure of the harmonic mean of precision and recall. These graphs illustrate that adding probabilistic noise during the training phase. So we've got the two phases, mode trained with no noise and mode trained with probabilistic noise. Improves all metrics because it results in a trained model less sensitive to anomalous time series inputs, and is therefore far less likely to have false positives. To demonstrate the effectiveness of the paper's model, the same data set was input into other popular anomaly detection models for ICS. You can see that performance in the data set, or in this chart. Specifically, those other models were Bloom filter, Bayesian model, or Bayesian network, support vector data description, isolation forest model. The Bloom filter used as a comparison, so the BF right there is different than the one used in the paper's package level anomaly detector. Just FYI. And then these last two. So those last two are Gaussian mixture model and principal component analysis with singular value decomposition. Both are unsupervised models, which means the training data set contains anomalies and whether or not, so it does contain anomalies, and then whether or not a package is an anomaly is not labeled. So from this table, you can see that the Bayesian network model and Bloom filter model are most like the model proposed by the paper, but neither are as adept at detecting anomalies. And then you've got the detected ratio of anomalous packages in each attack type. So your detected ratio of anomalous packages, recall in each attack type. So it breaks it down by the different attack types, and of those packages, of those attack types, how each model performed against the recall metric, which is listed there. This paper put forth an anomaly detection framework consisting of a Bloom filter package level anomaly detector and an LSTM network-based time series level anomaly detector. like mini deep learning frameworks, or like mini deep learning frameworks. It requires a large data set to train models properly. It is able to learn normal behavior solely from normal data, meaning it can alert on not yet seen attacks. Deal with complicated data samples that have a myriad of features. The training for it is straightforward, and the paper demonstrates that it has high performance, which we saw from the gas pipeline data set presented in the paper, and subsequent comparisons that they make against other ICS IDS frameworks. Looking forward, the authors speak to their research they want to continue to do. They mentioned testing with larger data sets. They suspect that their framework will perform even better given a larger data set, and that larger and more complex data set will allow them to use more complicated neural networks such as convolutional LSTM networks. And then they want to design approaches to dynamically adjust framework thresholds based on previous predictions.